I'm just going to check to make sure. Yep. Okay, so we can do the screen share. Desktop 2. All right, so it's being shared and it's recording right now. So we are good. We're ready to go. All right. So the first thing is, okay, how many people read this module? Okay, because I sent you guys a link. Okay, sort of. So what do you guys think? I think this is a great way to explain summation by defining it recursively. So I'll go over this just a little bit because I think it is really kind of important, especially if you're taking CISP440 in the same semester, because CISP430 has a lot of recursive definitions. And this one is one way of looking at things in a recursive way by breaking a big problem into smaller ones. So, so I think we're going to spend a little bit of time to talk about it today. And let me let some people in.
No.
What?
This is a module that you know.
Sorry?
This is a module that you know.
This is sent to you by announcement. So if you look through your announcement in Canvas, you should find it. And I'm just double checking to make sure that I have everybody in. Yep. So, okay, Omer is in. Okay.
Is the reading sum?
No, this is just a regular sum. Okay, so we'll start with this one here as a warm-up exercise after the spring break. All right, so we want to understand, what the sigma notation is about. Most of you should know it already, but I want to define it in a recursive way so that later on I can also define the pi, which is multiplication, using the same concept. And then we can also use the same way to explain what is for each, which is our for all, the universal quantifier, as well as there exist, which is our existential quantifier. So we can use the same approach to define those other, what I call big operators. All right, so we'll start with the easy one, which is this one. It is asking about what is the summation. That's what the sigma is representing, is the summation, where the index I is going from 2 to 5. And then the expression that is giving us the value to sum over is I squared. So in this case, because I is going from 2 to 5, that means we are adding 2 squared and 3 squared, 4 squared, and 5 squared together. And those things become 4, 9, 16, 25, and the summation is 54. So do we have any questions about this example of the sigma notation? Yep.
And summation is always an additive.
Oh, summation is addition. Yep. So when we ask about the sum of something, we're asking, what is the result of adding a bunch of stuff together. So summation is indeed implied by, addition or the other way around. So in general, the sigma summation notation is blah, blah, blah like this, where I abstract, in this case, I abstract out where we start, where we end, and what is each term that we're adding in the summation. So instead of saying, oh, this is I squared or I cubed or whatever, I just say it's some function of I. So are we still doing okay so far with the notation? Okay. So in our previous example, we can think of B being 2 because that's our starting point. E is 5, that's where we stop the summation. And f of I is I squared because that defines what each term is when we're trying to add all of those terms together. So generally speaking, summation is difficult to define because of the way it expands. So I can use examples to illustrate what I'm trying to explain, but it is difficult to use an actual hard definition to explain what summation is, because it's the expansion of a bunch of stuff. And it's really kind of not easy to explain, the expansion of a series of numbers, or in this case, the application of function f. So we'll try, using a different way. So we'll start with, what if b is greater than e? Well, since b is supposed to be the starting point, it's supposed to be less than or equal to e. So when b is greater than e, then we can basically say the summation has a default value of 0. And that's because 0 is the identity of addition. Okay, so how many people understood what I just said? 0 is the identity of addition. So if you don't understand, the first thing you probably want to consider doing is to raise your hand and go like, I'm not really sure what you mean by that. Okay, that's a yes.
Not really showing.
Applause. Okay, very good. So that is the first thing you should do in any class, not just in my classes, but in any class. The moment your professor says something that you don't fully comprehend because you have not been exposed to that concept, is to raise your hand and let your professor know. Now, how your professor is going to respond depends on the professor. It also depends on the subject matter, but you should let your professor know about that. Okay, so getting back to the statement, 0 is the identity of addition. What that means is you can add 0 to a value as many times as you want. It does not change the value. A plus 0 is A. B plus 0 is B, and so on. Is that okay? So you know that already, right? You know that adding 0 does not change anything. You just have not been exposed to the term that 0 is the identity of addition. Okay? All right, but it becomes important later on, okay? What is the identity of a particular operator becomes really important because we can look at the same kind of concept and abstract it up a little bit, and then we can apply the same concept to different things. Yes?
So by that logic, one would be the identity of multiplication.
One is the identity of multiplication. True is the identity of conjunction. False is the identity of disjunction. Because you can say, some Boolean value or false. Well, you're maintaining the same value. It doesn't change it. You can say some Boolean value and true. You're preserving the original value. You're not changing it in any way. So that's why those are all called the identity specific to a particular operator. Very good. Okay. So so this case here takes care of the weird case when the start value is greater than the end value. Then we can think of the special case when they are indeed the same. So when B and E, so when the starting point and the ending point are exactly the same, you have one single value in the entire summation because you only got one value, that you can apply F to. So in this case, when B and E are exactly the same, then the sigma notation is going to give you exactly the same as F of B, which is the same as F of E because B and E are indeed the same. So we're doing okay so far with the second case. Okay. So now we can make it even more general. And we can now say, let me see, did I make a mistake here? I think I did make a mistake here. When B is less than E, then the sigma notation is F of B plus the rest. Okay, so let me make changes to the note first because this is incorrect. Go back to 0382. And this is where we meet. Oh, that part is not wrong. I'm looking for this part here, which is the equation right before that. All right, so I just made some changes because the original one is incorrect, and I try to just fix the two. All right, so let me see if I indeed changed it. This is supposed to be less than E, and I thought I changed it. I did not. Okay, let me do that one more time. This changed in my notes. So why is it not doing? Just give me a second here because I need to fix this. More time, Control-Shift-R to refresh. And it is still not changed. It is the right module. I'm sorry for doing this, but I don't want to leave my notes incorrect. But if it's not changing, then I'm gonna have to just tell you guys, just imagine that thing is a less than and then move on. All right, well, I did change this correctly. All right, so if you look at this greater than here, just think of it as a less than because I messed up this one, okay? So if you think about the B is a less than, so we have B is less than E implies this thing here is f of B plus the rest of it. Is that okay? You'll just kind of imagine that greater than is actually less than because I kind of messed up and I cannot figure out yet, why it is not updating on the screen because I did change the source document. So this is the really important part because this is where I break a larger problem into something that can be solved right away and a smaller problem. Okay, so are we getting that concept? Because what we see here is B is less than E, which means there are at least two values that we have to sum over. Okay, so remember, this is supposed to be less than, not greater than. So now we look at the summation of I starting from B going to E, f of I. We break out when I equals to B to be its own term outside of the sigma notation. And then the sigma notation is now only responsible for quote unquote the rest of the terms to add to the sigma. Is that part okay? Because I'm just going to pause here because this really is the most important part of this entire discussion. Are we doing okay so far with that? Okay, all right. So you can see how this one starts with B, this one starts with B plus 1. Because the case of I equal to B is taken care of by just using, we'll just use f of B over here, and then the rest is starting with B plus 1 all the way to E. So this is the recursive definition here because we started off with a sigma notation. We end up with something that is not a sigma notation and the sigma notation itself, but when we reapply the sigma notation, the problem is one size smaller. Is that okay? All right. So when we combine the special condition, when we end the recursion and the case where we do have the recursion, then we have a general equation of the sigma or the summation of I starting from B ending with E f of I is a ternary expression, which basically is saying if B is greater than E, we just return a 0. On the other hand, if B is less than or equal to E, then we break up and say, okay, let's peel off I equal to B all by itself. So it's just f of B. And then the rest of it is going to be in the sigma notation again, but this time we start with B plus 1 instead of B, but it's still using the sigma notation. All right, so I'm going to pause here and see if there are any questions, up to and including this definition of the sigma notation. Are there any questions? Oh, you good? All right. So I think this is important because once we can use a recursive definition to define sigma, then we can use this part here is really just applying this definition recursively so that we end up knowing how to expand the sigma notation of I starting from 2 ending with 5 I squared. So we just do it step by step by recursively applying those definitions. So is that okay so far? That about this part here, it is just a recursive application of what we defined up here. So we good? All right. All right, so now we proceed to talk about the other big operators. So the first big operator is the pi operator, which is the product. So pi p, is product, sigma, which is s, is sum. So the pi operator is about multiplication. So you can see how the pi operator has about the same format. We start with b, we end with v, we end with e, and the terms that we are multiplying together is once again f of I. Okay. So the definition is, oh, okay, you see this is familiar, right? B is greater than E. It doesn't make sense, okay? Why would the starting point be greater than the endpoint? Well, in that case, return the identity of the operator. Because pi is about multiplication, the identity of multiplication is 1. Because you can multiply anything by 1 and get itself back. Is that okay? So instead of using 0, which is the identity of addition, we use 1, which is the identity of multiplication. Yes.
Is this kind of like an exponent that depends on what's at each index? Because like an exponent is like 2 times 2 times 2 times 2. This is like,
Well, you can use this notation. If f of I is just I itself, then it is about the same as factorial. Yeah, because we are multiplying all the f terms. So in other words, you can look at this as f of b plus f of b plus 1 plus times f of b plus 2 all the way dot to f of e. That's how you expand it. But using a recursive definition, this is how we can define that. But the rest of it is exactly the same. So structurally speaking, it is the same thing as what we had before, because what if b is less than or equal to e? Then we actually do have some term, at least one, to report back. So in that case, we have f of b kind of peeled off from the original pi notation. The rest of the pi, starting with b plus 1 as the next term, is still in the pi notation. But that's the same as what we did with the sigma notation, because we just say, we'll take the first one off, the rest is still in the pi notation. Are we doing okay so far with this? We have seen this already. Remember the practice exam for exam 1? When I used the G function to encode a string into a single number, a single natural number, it uses something like this, okay? It's just that instead of using multiplication, we were applying the G function to combine the result and a particular character. So for disjunction, so you can look at disjunction as a big operator too. So in this case, we have the or the disjunction of f of I, where I starts with b, ending with e. So in this case, when b is greater than e, then we return the identity of disjunction, which I talked about a little bit ago, because it doesn't matter what your Boolean value is. If you say that Boolean value or false, you get the original Boolean value back. So that's why we are using 0, which is represented false in this case. And then the rest is exactly the same. Structurally speaking, it's exactly the same. So we're still doing okay so far with the big operator. Yep.
so is this just another way of mentioning disjunction? Or
It is the disjunction of a bunch of stuff. And that bunch of stuff is represented by f of I, where I starts with b, ending with e. So this is basically the same thing as f of b or f of b plus 1 or f of b plus 2 or blah, 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 all the way down to f of e.
so we have disjunction, conjunction. What's the top one? That's just straight up multiplications.
This one is multiplication. It is the product of all the f of I terms. This one is the or of all the f of I terms, and this one is the end of all the f of I terms. So structurally speaking, they are basically the same thing, even though each one is using a different operator. Are we still doing okay so far with all of this stuff here? Okay. So now we're going to put a spin into this thing. We're going to throw a wrench into a running engine and see what happens. And turns out nothing really happens, okay? So we look at the existential quantifier. There exists an E in X such that f of E is true, okay? So we're basically asking, of all the elements of X, is there at least one element in X that f of E is true. That's basically what we're asking. So it is sort of, okay, I'm gonna say sort of. It's sort of like, asking what is the big OR notation of, for every E in X, for every element in X, we just want to do an OR of every single F of E. So it's really is the same thing. But once again, we don't have a definitive way of saying, how do we know this is, saying, okay, for instance, if X as a set has elements of 1, 2, and 3, okay? It really is asking F of 1 or F of 2 or F of 3. That's what it's asking, okay? But we don't have a way to iterate through because things are not inherently ordered in a set. We cannot say the first thing in the set, the second thing in the set, the third thing in the set, because they're not ordered, okay? So how can we express the fact that we're performing the same operation to all the different elements of a set? We do not have the vocabulary to express that. Until I invented the D of X notation. So let's take a look at what the D of I notation says. So D of I, okay, so we create a new notation, D of X, to deterministically draw an element from a non-empty set X. So what that means, if X is non-empty and you apply D to the set X, it always returns exactly the same element. That's all it does, okay? It is a very deterministic function. You give it a particular set, you apply the function to the set, it always gives you the same element. That's all it does. Is that concept okay?
So what is the point of this function?
What is the what?
What is the point of this function?
Well, it's a helper. Okay, this is a little helper function, so I can express the same thing like before, but this time it applies to. Let's do this to all the elements in the set, which we lack the vocabulary to express earlier.
But it doesn't change anything.
Huh? It does not change anything. So if you think about the attendance of this class, okay, as an example, okay. So if the same people are in this class and apply D function to the people in this class, it always picks exactly the same student every single time. Now, on the other hand, if we add one more person to this class, then it might change which person it is selecting out of the entire class, but it will still be deterministic. Is that okay? All right. And we don't even care, which element is picking, because the way we're going to use D of X makes it irrelevant to even have to know which one is going to pick out of X. We just have to know that it picks the same element out of X every single time. Are we still doing okay so far with this D of X? All right. So now we have this notation here. So I know some of you are thinking, aren't we going a little overboard in terms of notation? I have to give you a little bit of background. I recently got a request from UC Davis to ask me whether I am okay with basically making my dissertation, putting it into the Creative Commons pool so that everybody can check it out, read about it. I cannot even imagine anyone that would be interested to read my dissertation. So I went back and kind of looked at my own dissertation. And my first question is, who is this insane person using this many symbols to describe stuff? Yeah, that was my first impression of my own dissertation. It's like, who did this? Who would do something like this? But it is important, okay? The notations are very important because this is how we can define something both precisely and also concisely, which is what programming languages are about. Okay, because that's, why is it so hard to learn the programming language? Because it is very exact, okay? If you get something wrong, if you miss a comma, if you use a comma instead of a semicolon, the program is not going to compile. So mathematics is kind of a language too, in the same way. All right, so we're going to expand this and see what this is trying to say. So the original statement is something that we should understand by now, okay? Which is there exists an element E in X such that F of E is true. That's basically what it's asking. Can we find an element in X such that F of E is true in the set X? And then we kind of casually, turn it into a big OR notation, which is like this. We're basically saying, oh, let's use a gigantic OR. So we apply F to every single element, and then we OR the result of all the results of applying F to all the elements. So that's what we talked about earlier, but it's a very kind of casual definition. It's not really exact. And then we turn it into something that is very exact and recursive. So the first thing we do in this case, we ask, is X empty? In other words, are you trying to trick me? Because if X is empty, I don't have to think about what the answer is supposed to be. So this is the first question. It's a ternary expression again. If X is indeed empty, the empty set, then the default answer is false. In other words, if you're asking, is there an element in this set such that blah, 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 and the set is empty, then you just answer false, okay? Because nothing fulfills the requirement. So in this case, 0 or false is the identity of this junction. That's why we use false. What makes it a little bit interesting is the rest of this, okay? What if X is non-empty? Okay, if X is non-empty, then we kind of have to say, okay, we have to evaluate F with at least one of the elements. So in that case, we use the new notation d of x, which basically says by the time we apply d of x, we already know that x is non-empty. Okay, so I'm pausing a little bit because I want you guys to kind of absorb what I just said and think at least in your head and ask, how do we know x is non-empty by the time we apply d to x?
It's because you're using ternary expression like an if else, and so you go through you check is X empty, and then if it's not empty, then we start calling the d of X.
So exactly, because this part here is corresponding to the else of the condition. So by the time we evaluate this part here, it means X is empty is already false, which means X has at least one element. Okay. So if X has only one element, then d of X has to be the only element of X, okay? But I don't even care whether X has one element or two or an infinite number of elements. I just have to say, okay, this is a deterministic function, and to pick one particular element out of X, I don't care which one it picks. And it will apply F to that particular element, that will give me an answer, either true or false, okay? And then it's going to do this regular OR. This is a binary OR, which means they have two sides. We're just ORing between two things. So it's ORing this entire thing, and it's also ORing the result of the big OR notation with the rest. What do you mean by the rest? This is E in, but this time it is X minus the set that has D of X in it. In other words, whatever element I picked earlier to evaluate with F is no longer in the remaining portion of the set that I want to apply the big OR operator to. So in that way, it is doing exactly the same thing as the sigma notation and also the pi notation that we talked about earlier. But so I hope you guys can see that, oh, so you're really doing the same trick to different things, except in this case, we need a d of X notation to apply the same trick. Yes, that's it, okay? We are basically doing abstraction on exactly the same pattern over different types of operators. Are we good so far? All right, so if we can do this with the existential quantifier, we can also do it to the universal quantifier. So the universal quantifier in many ways is quote unquote the opposite. So wherever we see a OR, it turns into an AND. Whenever we see a false, it becomes a true. The OR becomes an AND again. The big OR becomes a big AND again. So it is really kind of quote unquote the opposite of the existential operator. Are we doing okay so far with this notation? Okay, so let me ask you this, okay? If, in terms of the, okay, maybe I should finish this last part here because I wrote it for a reason. Is this really necessary? In other words, to many people, this can be perceived as making things unnecessarily difficult. And it would not be the first time people use that to describe the way I teach. But the question is it really the case? Well, the answer is no, because if I see this as unnecessarily difficult or complicated, I would not have put it here. I put it here for a reason. In fact, there are two reasons. The first reason has to do with the notation. There's no better way to explain summation, because all of the other ways will give you a ... notation. Okay, so you kind of have to imagine, oh, so we are extending this thing here to cover all of the things within the range from B to E. That is not very exact. Okay, that's kind of like, well, I mean, you can understand it as a person. You can kind of go through some examples and kind of get the idea. But this definition, the recursive definition, is exact. You can turn it into code. By preserving the structure, you can turn it into code. But there's a second reason too. The second reason is this is an example of recursive definitions. So if you can understand how to derive recursive definitions, you would also understand how to derive recursive functions in C and C++, which is also what you're learning now in CISP440. So what topic are you guys on in 430 now?
Trees.
Trees, okay. Isn't that recursive? Every branch of a tree is a tree on its own.
I mean, I'm thinking of BSTs, that's why I'm not really.
A BST is a tree. Every tree is recursive. Until you get to a node is just a really, really deformed tree. It is nonetheless a tree. And that's why when you have trees, you have recursive algorithms to get things done.
That's actually.
Yeah, the traversal of a tree, the construction of a tree, all of those can be done recursively because a tree is nothing more than a node. And if you do have children, the children and each one is a subtree. So you basically just do the recursive call to each of the subtrees, depending on what you're trying to do, right? Sometimes you only have to do it to one of the children or one of the subtrees. Sometimes you have to do it to all the subtrees. So depending on what you're trying to do, but nonetheless, the algorithm is still recursive. So those are the reasons why I want to I made this semester because I just thought about, hey, I can explain summation in a recursive way. But there's a reason why I want to talk about it in a recursive way. So are there any questions about this particular module? No? Okay. There's actually a third reason why I made this module, because I still have people asking me what is the meaning of the existential quantifier and also what is the meaning of the universal quantifier. This way, I have a definite explanation of what it means to be for each blah, 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 and also there exists blah, 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 because now it is definite. So are we good so far? This is a little digression from the usual lecture, but I think it is a useful one. The questions? All right. Yep.
What you mean by E, you mean 2.7, right? Or any variable? Because when I see the exponential operator.
No. The E is really nothing more than just a variable in this case. It's not the Euler constant.
It is confusing.
It is?
It is confusing.
I'm not a mathematician, so it's not confusing to me because when I use E, it is nothing more than just a letter. Where do you see the exponential thing?
Well, every time I see someone use E, it always means 2.7.
Oh,
I've never seen it used in a case. I'm like, I swear this is every variable, but I could be wrong.
okay. This is intended as a pun, so I want to kind of prefix everything so that people don't misinterpret me unnecessarily. This class is called discrete math, right? E is not discrete.
Right.
Which is not to say it is indiscrete, it simply means it is irrational. There's a difference between irrational and indiscrete. Okay, one describes people, one describes certain types of numbers. Yes.
I was concerned.
Because I don't want any mathematician or math professors coming here and going like, are you calling us indiscrete? No. I'm just calling your numbers irrational, not even you. just your numbers being irrational. Okay, fun, just puns, okay,
It's not a bad thing for numbers.
being irrational.
Yeah.
How about being imaginary?
Oh, that's interesting.
How are those, how are imaginaries put in computers actually?
Okay, let me answer his question first, and then we'll get back to the imaginary number. Yep, go ahead.
So with the dx of the functions, how would we put that into a form? Because if it's just picking some element in the set.
That's a good question. So the question is, how do we implement, right? You're talking about implementation. So if we implement set as a data structure, how would we create the D function? Is that kind of what you're asking? So in every way you create a representation of a set, there is usually an inherent order to the underlying representation. So even though as a mathematical concept, a set has no specific order, when you actually implement it, there is usually a way they can say, oh, if this is going to be the first element that I encounter. So we can just pick out the first one in that case. All right. Oh, getting back to the imaginary number thing. So imaginary numbers typically in discrete math, in what we are talking about here, it doesn't have a whole lot of usefulness, but it does have usefulness when you do signal processing. So signal processing, yes. So if you want to do audio, compression, then complex numbers become really helpful. So that's one application. And then the other big one is quantum computing.
I thought it was for matrices flipping.
Hmm?
To rotate a matrix.
To rotate something, you do not need complex numbers. You just need a 3x3 matrix.
Yeah, but how would you rotate it? Like modify it so it's rotated?
That has to do with sine and cosine.
Oh, okay.
Yeah, which can be expressed using, e to the power of an imaginary number, or e to the power of a complex number. But if you want to understand quantum computing, then it is crucial to understand complex numbers. Yep.
Didn't they use that to figure out that it's possible for wormholes to exist?
What? Say it again?
Because like, isn't quantum computing good for solving certain physics that are so like complicated that it'll take like a quadrillion years to solve or something?
That I do not know. Yep. All right, so now we return to our regularly scheduled program. So we took a little digression, but I hope that digression is helpful in some ways. I had 3 reasons why I went through that digression, but now we're back to the regularly scheduled program. So we're going to resume our discussion using resolution. And this is what we talked about before the break. Okay, so if this looks entirely new to you, you might need to do some review because we did talk about resolution before. So this is a proof of resolution itself is a mechanism that works. Okay, in other words, what is true here, all the way out, all the way down here, what is true here is this implication. This implication is always true, regardless of what you choose to be your phi, your psi, and also your rho. So pick whatever you want, okay? As a Boolean expression, pick whatever you want as your phi, your psi, and your rho. This implication is always true. Is that okay? Okay, that's what this proof is trying to prove. So when we apply this theorem in terms of deriving the truthfulness of proposition, then what we want to do is to say, well, what if psi is a single variable? And then phi is a disjunction of constants, variables, or negation of variables, and same thing with rho. So when that happens, then we have a mechanism to prove theorems in a way where the haystack is no longer infinitely large. You guys still remember before the break, we talked about how we're trying to find a needle, which is the theorem that you want to prove in a haystack that is infinitely large. So the problem is you cannot tell whether the needle does not exist in a haystack, which means what you're trying to prove cannot be proven, or that you have not found it yet. Okay, so that's the problem. So if we use a different mechanism, we can actually make the haystack finite. So once the haystack is finite, it becomes a whole lot easier because you can just look at every single thing in the haystack and say, did I find a needle? It might take you a long time, but it is deterministic. Now you can actually have a definite answer of whether the needle is in the haystack or not, because the haystack itself is now finite. So the first step to do that is to change the propositional calculus system that we have been working with, and we are simplifying it, okay? We are not making it any more complicated. We are just simplifying it. So the way we simplify is to say, in terms of operators, we just have negation, Boolean negation. In terms of binary operators, we have one single thing left, which is just regular or. That's it. We don't need implication. We don't need equivalent to. We don't even need and. Okay, so we just have or left. But the way we define is a well-formed formula is changed a little bit. So I have to introduce, this is a disjunctive element is ADE as a predicate. So everything in alpha is automatically is a disjunctive element. In other words, it can appear in a disjunction. Is that okay? So you pick anything out of alpha, which is the set of all the alphabet that we can use in the system. Every single one of those qualifies as an element that you can use inside a disjunction. And on top of that, we can also say, in addition to that, we say the negation of anything in alpha also qualifies as something that you can use inside a disjunction. Is that part okay too? In other words, if you have PQR in alpha, then PQR, each one can be used in a disjunction. You can also use not P as an element inside the disjunction. Not Q can also be inside the disjunction. Not R can also be inside a disjunction. Is that okay? So your disjunction can only be a disjunction of things in alpha or negation thereof. All right. So with all of that done, then we have this notation here. So once again, it is important to know how to read universal quantifiers, because in this case, I basically say, assuming we have a set from 1 to n, 1, 2, 3, all the way up to n, and I is an element for every element I in the set of 1 all the way up to n. If phi of I is a disjunctive element, in other words, I have n disjunctive elements. Phi 1 is a disjunctive element, phi 2 is a disjunctive element, all the way up to phi n, which is also a disjunctive element. I have n disjunctive elements. Each one is either something in alpha or negation thereof. Okay, that's basically what each one of these n things are. Then I can say, if you make a disjunction of those n things, that is now a well-formed formula. That's it. All right, so let's take a look at some examples, okay? Because I think examples can help us understand what do we mean by a well-formed formula using this modified version of so let me okay, I want to maximize this too. Okay, so maximize. There we go. All right. So you guys can focus on the other side, and I'm typing on this side here. Okay. So let's say, so I'm going to define alpha first. Okay, so we'll define alpha to have just P, Q, R, S, T. Okay. So if alpha is P, Q, R, S, T, or is the set of P, Q, R, S, T, then we can have is a W, F, F. And this time we have not P or Q. That is true. Okay, it's true. Because in this case, we have a or, and then all of the things that we are ordering, each one is either something from alpha directly or the negation of something from alpha directly. Is that okay? All right. And to be consistent with the notation, is a WFF should not be italic. So let me just fix that first. Just fixing the font. It's not important, but it is good to be consistent like that. Okay, so this one is done, and we'll take a look at another example. So this time we're going to use the negation, but the negation is not on top of just P. Instead, we have P or R inside the negation. This one is not well formed. Okay, so let me just double check with everybody. Does everybody understand why not in parentheses P or R, the whole thing or Q is not well formed? Because it is not a disjunction of things that are directly coming from alpha or negation thereof. Because one of the things in the outer OR, if you look at this OR here, one of the things is ORing is okay, that's Q. But the other thing is ORing is the negation of something that is not directly from alpha. And that is why in the second example, it is the expression is not well formed. Are we doing okay so far with this? All right. So let's show another example that also has 3 items. So I can do something like this. Oops. And this one is indeed well formed. So this one is well formed because it is a big OR of 3 things. What are the 3 things? R is coming from alpha, okay. Q is coming from alpha, it's okay. Not P is the negation of something from alpha. That's why it's okay too. Is that okay? I'll give you guys one more example, okay? If you have more questions, we'll go ahead and answer those additional questions. All right. So this one is not well formed because we have one thing that is being negated, and this is the negation of a bunch of ORs. So without the negation on the outside, yes, we have something that's well formed, but the negation of that thing is not well formed. Are we doing okay so far? I mean, do you guys want me to go over some of your own example? Because that's one way to ask questions, is to say, okay, what about this thing that I just constructed? Is it well formed? Yeah, you want to give it a try? No, okay. Yep.
So we established that we have the or, so we can't say that P or V.
P or V
That's
is
a-
well formed. Yeah.
But so the negation of P or V or Q is false. So
Which one? Which,
sorry, the second AWF.
the second one? So you're talking about this one?
Yes, so we know that
Because we have an or here. The question is, what is it oring? The right-hand side is fine because Q is indeed something that we can find from alpha. But on the left-hand side, we have a problem because we have a negation of something, and that something is not directly from alpha. It is an expression that you can form using things from alpha and also from omega, but by itself, it is not something that you find in alpha itself.
so the other things are P plus T and its negations. And that's the only valid thing.
PKRST or negations thereof. Yep, so you have 10 possible choices in your gigantic, or you have 10 choices. Why? Because we have PKRST as 5 of the choices. Then we have not P, not Q, not R, not S, not T as the other 5 choices. Are we still doing okay so far with, what is the new definition of what is considered well formed? This is a lot more restrictive compared to what we dealt with before. Are we okay? All right. I just want to make sure. All right, okay. So let me go back to the notes again. So the question is, okay, so let me ask you this question, okay? So why do you think, we want to convert everything to this particular format? Let me go back to here. So why do we want to convert everything into something that looks like this or something that looks like this? So tell me again, how are things related in iota? What is the purpose of the set iota in propositional calculus? First of all, what type of thing are in iota? What do they look like? Go ahead.
Axioms.
Axioms, but each axiom looks like what? It is a
Well-formed formula.
well-formed formula. Okay, very good. So the next question is, if you have more than one element in iota, how do they relate to each other? Are they related because of an or operator, like at least one of them has to be true? Or are they related using a conjunction that all of them have to be true? All of them have to be true. So they're all connected inherently by a conjunction, right? So if every well-formed formula looks like this, the first one or the third one like this, then you have what we call a CNF, a conjunctive normal form, because you have a conjunction of disjunctions. And inside each disjunction, you have either something directly from alpha or something that is the negation of something from alpha. Are you okay so far with that? So that prompts the next question, which is, how does this has anything to do with what we started off with, okay, after the discussion of the quantifiers? Remember, we started talking about resolution, right? So what does this has anything to do with resolution? Remember, we now have a way to express everything that we know to be true as a conjunction of disjunctions. Inside each disjunction, we have either an element of alpha or we have the negation of an element from alpha. So what does that have anything to do with resolution? So let's go back to the definition of resolution and see if you guys can tell me where the connection is. So with resolution, the proof itself is not important at this point. We're only looking at the implication itself. So from this implication itself, why do you think the way we define what a well-formed formula is now becoming important?
You can combine it with new ones.
You can combine them to make new ones. Okay, that's very good. So if you look at, okay, I'm gonna use a mouse pointer here. So if you look at this thing here, if this one does not put any restriction of what phi can be and what psi can be. But in your mind, you can think of, what if psi is restricted to a single item, single element from alpha, and then phi is just whatever disjunction is left over in a well-formed formula under the new definition. Okay, and then the other one on the right-hand side of the and, this is the same thing. Okay, so now we're looking at this and go like, psi is an element of alpha, so not psi is just a negation of an element of alpha. And then rho can be the leftover of the entire disjunction, whatever it is, right? So what is the result of this? It implies, okay, what does it imply? It implies phi or rho. What just happened to psi? What happened to that one element of alpha that we use psi as a variable as a placeholder? It disappears. So you can start with more variables, and the result of applying resolution is the reduction of the number of variables. Is that okay? So if
So you create a new well-formed equation, get rid of an old one.
it is implied by the old ones. So you have two well-formed formulae. This one, psi or phi or psi is one well-formed formula that is known to be true at some point. Okay, it doesn't have to be in iota. It can be derived from iota. Okay, that's the whole point. Is each one can be derived. And then we have not psi or rho, which is another well-formed formula that can also be derived from iota. It can be from iota itself, but it can also be derived from iota. Okay, so now you have two well-formed formulae that were both derived from iota. If they are both present, and you can say that, oh, one has a variable from alpha that is not negated, the other one has the same variable from alpha, but it's negated. Then you can say, I can now concatenate the rest of the first well-formed formula, the rest of the second well-formed formula, make a new well-formed formula, and that one is now also derived. Are we doing okay with that concept? Okay? Yes or no? Okay? So what is the big deal? I mean, we can construct, we can use implication all day long, because, P can imply P and P, right? P and P can imply P and P and P and P and so on. So what makes this one special? Because the result is always simpler than what you started off with. Does that make sense? So yes, go ahead.
Concrete example?
Yes, we will talk about concrete examples, but right now we're just looking at the connection between resolution itself and the way we define the what is considered well formed. Yep.
Are you trying to say P is a simple equation solved in size?
Say that one more
P is a
time.
simple equation solved in size, is that what you're trying to say? Or not?
The result is a simpler, it involves one fewer variable. This is the result. It has one fewer variable compared to what we started off with. Which means, if you think about this, if we keep applying the same thing over and over again, some of you, I hope, is thinking about, so maybe at some point we'll have nothing left. What happens when we have nothing left? So that's the question, okay? What do you think? What do you think when we have nothing left?
Infinite solution?
No. Okay, so let's think about the very deformed disjunctive expression, okay? So if you think about, this phi here, the question is, what can phi be? Phi can be a long disjunction of stuff, but what is the simplest phi you can possibly make in order to make a disjunction of things? Remember what we talked about in terms of identity? What is the identity of disjunction? What is the identity of disjunction? False. False, very good. So that means a very deformed disjunctive expression is false or a single variable from alpha. Is that okay? On the other side, it's the same thing, okay? Rho can be false, which means we have not psi, which is not some variable from alpha, or false. So what happens when you apply that resolution? Okay, let me just write this out because I think it's getting harder for people to kind of. Yep. So let me write it out because then you got it, but I do want to kind of write it out so that people can actually visualize and see it. So we can now have a situation where you have false, or we'll just pick P from alpha, okay? So on one side we have this, and then we have the conjunction with another disjunction here. The other one is going to be the negation of P or false. So using the resolution, what does this imply? Let me see. I need to remove this space so it shows. So if you, okay, first of all, does it look like resolution can be applied here? Do we have a pattern where resolution can be applied? Okay, we have or and or, okay, we have an and between the two disjunctions. So far so good. What is inside each disjunction? This thing has an or, this is the remaining portion. The fact that it is just a constant of false doesn't matter. Okay, we just look at it as quote unquote the rest of the disjunction. The most important part here, it has a P, which is from alpha, okay, as one of the components inside the disjunction, right? The other one has not P in it. So according to the rule of resolution, we can now say, we'll just have a concatenation of whatever is left over, which is just false or false. Does that make sense to you? This is a very special case of applying resolution, but nonetheless, it still applies.
So it's like the base case for recursion. So it's like the base case for recursion.
It is not recursive in this case, because in this case, what exactly is false or false?
It defines that we have reached the end.
Say that again?
So it defines that we have reached to the end, like you, I told you.
It is an and, but it's not in a recursive sense. Okay, it is an and. So false or false is known as just false, right? So are you telling me that by combining all the things in iota and also all the things that we can derive from iota, we end up with false? That doesn't make sense, right? Because everything that can be derived is supposed to be true, and we end up with something that is false. That doesn't make sense. What are we trying to do here? Remember the three ingredients that we talked about before the break? I know most of you are going to say, no, are you really expecting me to remember? Yes, I am really expecting you guys to remember. But I can also remind you what those three ingredients are, okay? One is resolution, okay? It is the logic mechanism to do all the things that we want to do. The second one is CNF. What do we need to change things into in terms of its formula in order to apply resolution? What was the third one?
Proof by contradiction.
Proof by contradiction, right? So how does proof by contradiction work?
You basically ask, is it possible for this to be false? No? Okay, then it's true.
Sort of, yes.
If someone's like, this is like proves is false, I'll start by proof, like, assuming it's true. And it's proof, like,
The other way around, right? The other way around. Okay. So proof by contradiction works in the sense that you have a bunch of stuff that is given, okay, which is our iota. Okay, the set of iota is everything that is known to be true, everything that is assumed to be true. And then you have a theorem that you want to prove. You basically want to say, if everything in iota is true, so that one has to be true too. That is what proof is. Proof by contradiction is trying to say, if you combine everything that you assume to be true and the negation of the very same thing that you want to prove to be true, if you combine those two things, you should come to a contradiction. So that means we start with iota the same way as before, but the way we introduce the theorem that we want to prove into this entire system is we negate it first. In other words, we poison the pool and see if someone dies. In order to prove that poison is indeed poisonous. So I just came up with this analogy. I'm not sure whether that works or not. But that's what we are doing here, okay? The three ingredients. So let me get back to this presentation here. So this contradiction here, this false here, is actually what we want, okay? Because what we're doing here is we are starting with everything in iota. Okay, so those things stay exactly the same as before. We have a theorem that we want to prove, but we have to negate it first, okay? So you negate the theorem that you want to prove, turn that into the WFFs that we have talked about, and you combine that with everything in iota. So that has to be proved, that you have to prove that entire conjunction is false in order to use proof by contradiction. So that's how the three things connect in order to work. So I'm just checking the time. We got 10 minutes. I can show you an example. Okay, I know you guys are dying to see an actual example. But nobody has to die because the example is actually in the notes. In other words, people are going like, I'm drowning in the pool. Try standing up. Oh, okay. I'm not drowning anymore. All right, so when you go all the way down here, there's an example. All right, so this is we assume this is true, okay? So this is a conversion using Boolean algebra to show that whatever we start over here ends up to be here, okay? The mechanism itself is not important, okay? So I just want to focus on the concept first. So this is an expression that eventually boils down to the same thing as this thing here. Are we getting that part? So for now, forget about the derivation, just accept that this particular Boolean expression really is the same thing as this expression here. Are we doing okay so far? So that means we can put not P or R into iota. We can put not P or not Q into iota, because these are things that are given to be true to begin with. Is that part okay? So we can start with an iota that has two specific elements. not P or R is one, not P or not Q is the other. Are we good so far? So now I'm asking you to prove a particular theorem, which is an expression, a Boolean expression, and I want to ask proof by contradiction. So let me I'm trying to skip to an example. This is the example. Okay, there we go. So this is the same expression that we had before. It turns into a CNF. So now we have a theorem. This is the theorem that I want you to prove. In other words, if I tell you ahead of time that not P or R has to be true, and not P or not Q also has to be true. Those things are given to you already. Okay. And I'm asking you, does that imply not P implies Q is also going to be true? This is the theorem. Phi is the theorem that I'm trying to prove. Okay, are we understanding the question first? Because we first have to understand what problem are we trying to solve in order for me to kind of illustrate the method that we're going to solve the problem. So
Not clear the question.
Okay, very good. So the question is, if psi is given to you, okay, I'm just telling you out of the blue that not P or R and not P or not Q is given to you to be true. Okay, don't ask me why, it is just true. Are we good so far? I want to ask you a second question. I want to ask you the question of, can we use that fact that psi is true to say that, oh, if psi is true, so is phi. Not T implies P also has to be true. Can I make that connection? That is the question. If I can make that connection, then we have a proof. If I cannot make that connection, then we have to say, phi is not a theorem. It is not a consequence of psi. Is that okay? So does everybody understand what problem we are trying to solve? Okay, so the method to solve it is to use proof by contradiction, which means we have to negate the theorem that we are trying to prove in the first place. This is the theorem that we are trying to prove in the first place, so we have to negate it first. So to negate phi is pretty easy. To say the negation of phi is the negation of not T implies P. Not T implies P expands to a disjunction like this by the definition of implication. And then using De Morgan's law, which I have to show because I forgot to talk about that. By using De Morgan's law, it becomes like this, and it is by itself now a conjunctive normal form. Are we doing okay so far? Is everybody buying that not T or not P is a disjunct, is a conjunctive normal form? In other words, I can now claim and say this is now a conjunction of disjunctions. It's a trick question because I'm expecting people to say, but I don't see any disjunction here, right? That's okay. You can kind of imagine that not T has an imaginary friend of false. So we have not T or false. Not P also have the same imaginary friend. So not P is really an expression of not P or false. So not P or false is definitely a disjunction, not a problem, right? Not T or false is also a disjunction. So yes, we do have a conjunction of disjunctions. Is that okay so far? All right. So now we make a, this is my term, a super CNF, which is combining psi, representing everything that is given to you to be true, and the negation of phi, but it is already in the same format as a CNF. In other words, we're looking at this first part here. This is psi. This is everything that is given to you to be true. Okay, don't ask me why. It is just given to you as true. We look at the second part here. This is representing the theorem that we want to prove, but it is the negated theorem turned into a CNF. Okay, so now we ask, can we apply resolution? So in this case, we cannot apply resolution, not even one single step. How do you apply resolution? Okay, we look at the first term, which is not P or R. So now we have to look for something else that has P that is not negated. Okay, I cannot find P non-negated, okay. Or we can find R that is negated. No, I don't see any R that is negated. So that means the first term cannot be combined with anything else using resolution. Then we apply the second term. Okay, look at the second term. We already know that not P cannot find P that to pair up with it. So we look at not Q and ask, can we find Q that is not negated? No, we cannot. So when you apply that logic to the entire thing, there's not a single step of resolution that you can apply, which means the theorem is not, the proposed theorem is not a theorem. In other words, this phi here does not follow the fact that psi is true. Is that okay? Psi does not imply phi in this case. I do not find a connection between those two. So let's find another example that shows you that what if it does, okay? So we have another example here. So this phi prime is a different theorem, it's a different expression. It is P implies not Q. So now the question is, can I prove that psi, which is all the way up here, this psi all the way up here, does psi imply phi prime? That's my question. But instead of proving it directly, I'm using proof by contradiction, which means the first thing I need to do is to negate the theorem that I'm trying to prove. So I negate phi prime first. So to negate phi prime, I have the negation of P implies not Q, which turns into the negation of not P or not Q because of the definition of implication. And then we apply De Morgan's law, it becomes not P or not Q, which then becomes, which then simplifies to P and Q. Is that okay so far? So P and Q is nothing more than the C and F, the conjunctive normal form of the negation of the theorem that we are trying to prove. Are we doing okay so far with the concept? So we are not focusing on the Boolean algebra at this point. We're just focusing on the concept of converting the negation of the theorem into a CNF itself. Are we good? Okay. So now we have a conjunction between psi and not phi prime. So now we combine these two. So now we have quote unquote the super CNF again. Once again, this portion here is representing psi, everything that you are told to be true. Yes.
I have a question about this law. Does the negation like negate even the operators?
It has to be applied to a conjunction or disjunction, but it doesn't have to be binary. Yep. Okay. So let me kind of quickly go over that first. Okay. So De Morgan's law basically says, P, the negation of P and Q is the same thing as not P or not Q. That's one side of De Morgan's law. And then if you flip all the N and Ors, it is also true. So if you have the negation of P or Q, it is the same thing as not P and not Q. That's De Morgan's law. So De Morgan's law has two components. Both of these are components of De Morgan's law. Yes.
They're no longer grouped together.
The parentheses, make it very clear how things are grouped. So even if it's not necessary, it does give you a sense of how things are grouped. We are not quite done yet. Let me go back here because I do want to get you to the end of this thing here. So with this one, we can apply resolution because I underline this. Okay, this is not P, this is P non-negated. So they combine. This is the leftover from the first disjunction. The leftover of this disjunction here is false. So when you combine these two, you just get not Q left. Is that okay? All right. So now we look at this Q and this not Q. We can also apply resolution because Q is the same thing as Q or false, right? Not Q is the same thing as not Q or false. The Q and the not Q cancel out because of resolution. So we end up with false or false, which is really just false. So this false here is really significant because this false is reflecting the conjunction between what is known to be true and the negation of the theorem is leading to a contradiction. So by proof of contradiction, we have just proven that phi prime is indeed a theorem. That's how all the pieces connect. So this example here, this specific example here illustrates how all three pieces connect in terms of concept. So I got one more thing. I know we are running out over time here. So these two, the last two lines here represent the Morgan's law. So when you look at this, if you're asking, I'm not really sure that is, that actually equality holds. What do we do to prove that? Yes, truth table. Okay, so if you're not convinced about the validity of the Morgan's law, I would encourage you to use a truth table to prove both of these equalities. It's a good exercise anyway, and it would also, you would come up, being super convinced that the Morgan's law does make sense. And it's a very, very useful technique in Boolean algebra. All right, so that concludes today's lecture. I will see you guys on Wednesday.